Hi everybody, let's start on chapter 32 of your intermediate physics text that's about inductance. So this is really related to the previous chapter. If you haven't completed looking through the previous chapter or watching those videos, definitely go back and do that. So my outline for my notes, we're going to first talk about mutual inductance, which is actually section 4 of your chapter in your textbook, then get into self-inductance, the energy stored in a magnetic field, circuits that involve both a resistor and what's called an inductor, that we're going to use the letter L for, systems that, or circuits that involve our inductor and a capacitor, and circuits that involve both an inductor, a capacitor, and also a resistor. So we'll talk about these three types of circuits, but first we need to talk about what is inductance. So if we review what we learned in a previous chapter, we saw that changing the magnetic flux through a current loop induces an EMF, or an electromotive force, and that electric current produces its own magnetic field. So we're going to make two predictions here. The first prediction is that changing the current in one circuit ought to induce an EMF, or an electromotive force, and a current because of that electromotive force in a second nearby circuit. So this is what's called mutual inductance. Prediction 2 is that changing a current in one circuit ought to induce an EMF in itself. That is what we would call self-inductance. So like I said, we're going to start out with mutual inductance. So we can picture our two coils, right? So coil number 1 has a current flowing through it, and maybe that current just starts or just stops or is changing with time. So if that current is changing with time, it's going to create a magnetic field that is also changing with time. So some of those magnetic field lines pass through coil number 2. So we're going to define for ourselves a magnetic flux that, rather than using the subscript B, since we know we're talking about magnetic flux, we're going to instead say magnetic flux through loop number 2 because of current number 1, right? So we'll call it Phi21. And so if that flux is through number 1 or number 2, and that coil number 2 contains N2 closely packed loops, we know that the EMF induced in coil number 2 because of the current in coil number 1 is going to be equal to N2, so the number of loops in number 2, times the flux that is going through number 2 and how that flux changes with time. Now, we're going to throw a negative sign on there because of Lenz's law, and that's just Faraday's law that we've already known. So if the two coils are fixed in space, that flux is proportional to the current I1 in coil 1. So this flux is proportional to the current in number 1 because the magnetic field that's created by coil 1 is proportional to the current that's in coil number 1. So that gets us to the idea of mutual inductance. So if our flux is proportional to the current in number 1 and we've got this EMF, we're going to have a proportionality constant that is our mutual inductance. So our proportionality constant is going to look like mutual inductance of 1 in, so the inductance in 2 because of 1, right? And it is going to be related to the loops through number 2, the flux because of current 1 through number 2, and that current in number 1. So in other words, we could rearrange that and write that the flux through loop number 2 because of the current in number 1 looks like this. So it's a proportionality constant. So if we look at that and then compare it to our previous one, we would get the EMF that is induced in coil 2 due to any kind of changing current in coil number 1 is gonna look like this. So I could substitute in and write, oh, we could just use this proportionality constant and talk about, let me write the right letters, and talk about the changing current in coil number 1 instead of just the changing flux, right? So what's interesting about this is that our mutual inductance, or that constant of proportionality, does not actually depend on our current. And I know if I flip back to a previous slide, you're going to say, but wait, you have in your equation there current, right? But remember, current is also contained in the information for the magnetic field that is causing this flux. So by dividing by I1, we've divided out actually the I1 dependence. And so our mutual inductance does not depend on our current. Instead, much like capacitance, it's going to depend on geometric factors. So the geometric factors that our mutual inductance could depend on are things like size, shape, the number of turns, the relative positions of these, and any ferromagnetic materials. So again, there is a parallel to our capacitance. So number of coils, or number of turns of coil, and relative position. What else did I say? The other thing I said was ferromagnetic materials. So if we put an iron core in either one of these coils or in both of these coils, that would change our magnetic field that we've created, and that would change how this mutual inductance works. Just like putting a dielectric in between capacitor plates changes the capacitance. So our mutual inductance is usually determined experimentally, and we can talk about the easy experiments that you would do to introduce this. So the reverse situation, you can look at this and imagine that if we did a reverse situation, so our reverse situation would be current in coil number 2 causing a flux through coil number 1. Right, that's an easy enough thing to picture. So a current in coil number 2 causes this flux through number 1. If we do that same situation, we would get this same relationship that looks very much like the one I've written above for coil number 2. So there, M12 is the mutual inductance of coil 1 with respect to coil 2. You can actually show that these two mutual inductance, these constants of proportionality, are equal to each other So let's drop the subscripts and just call it M for mutual inductance, right? And so with that, you can get to the fact that your induced current, or your induced EMF rather, in coil number 1 is just due to a change in current in coil number 2, and your induced EMF in coil number 2 is due again to a change in current in its neighbor, coil number 1. The SI unit for our mutual inductance is named after an American physicist who was actually the first guy in charge of the Smithsonian. So there's your trivia for today. The unit is called a Henry, and 1 Henry is equal to 1 volt seconds, that's my capital V, per ampere, or you could say 1 ohm times second. Those units are all mutually equal to each other. All right, so let's do an example with one. So let's say we have a solenoid and a coil, and this is very similar to an example in your book that talks about how your wireless charger works for an electric toothbrush, right? So in this case, we've got a long, thin solenoid of length L and cross-sectional area A. It contains N1 closely packed turns of wire. Wrapped around it is an insulated coil of N2 turns. Assume all the flux from coil 1 passes through coil 2 and calculate the mutual inductance. So let's sort out what we're given here. So we've got a long, thin coil that they're giving us all this information about: length L, cross-sectional area, and turns. So that's our first set of things that we want to write down. And then we want to separate out our second coil with N2 turns. And we're saying all the flux from coil 1 passes through coil 2. So what we're actually going to do is we're going to say that this long, thin solenoid has a magnetic field. All right, so we know the magnetic field from solenoids are going to look like this. All right, and remember, so this is our coil 1. And remember that this lowercase n that we have in our solenoid equation in most cases is just the number of turns per unit length. So if we're just given total number of turns and a total length, we can assume that they are stacked evenly and that we can do that kind of math. And then we also want to say that I1 is that current in our coil 1. All right, so let's take this to the next page. So we've got an idea of what the magnetic field should be. We're also going to make the assumption that our flux through our second coil, because of our first coil, is going to be just B times A. So I'm making the assumption that I can take my dot product and turn it into simple multiplication, that these two are stacked on each other and their areas are in the same direction. So I want to do this kind of math. This is my B from coil number 1. And then we need our area from coil number 2. So we can spot right here that we can take this and figure out our mutual inductance. So our mutual inductance, remember, should be, so we're looking at because of coil 2 on coil 1, or other way around, because of coil 1 on coil 2, right? Our mutual inductance should look like that. So if we take this and put it in for our flux, our mutual inductance is going to give us the equation mu 0 N2 N1. We're divided by an L and we're multiplied by an A. So what's interesting about this is that it does not depend on I. Here's our answer. So just to reiterate what I said before, our mutual inductance doesn't depend on our current. It just depends on these things like mu0, n2, n1, right? So these geometric factors. And if we go back and look at our image, I'll draw it kind of badly. So say we had that long solenoid that was our coil 1. Remember, for coil 1, the magnetic field, if it's a solenoid, it exists within this coil, right? And it branches out here at the ends. Our drawing had coil 2 out around coil 1, right? But away from the ends. So here's our coil 2. We're going to call this the area because that's where the magnetic field exists that is causing this flux that is making the EMF induced in coil 2. It is worth noting that unless there are many, many turns or there's an iron core involved, the mutual inductance is usually pretty small. If you want to avoid mutual inductance even more, a shielded cable can reduce undesirable inductance as well. I believe there's an example in your book about coaxial cable talking about that. So we want to move along to self-inductance. So self-inductance happens when a coil creates its own magnetic field and resists the creation of that field. So let's look at the example here to the right. We've got a single isolated coil that when a switch is closed, a current starts to flow. And here in this chapter, you'll notice they start using a lowercase I for current. I will continue to use the capital I probably, just out of habit. After the switch is closed, a current starts and that creates a magnetic field. Now, part of this magnetic field for this wire, you can see, comes through the center of that current loop. So changing the current through a coil gives a changing magnetic flux inside the coil. So we change the current through the coil, we're going to change that magnetic flux through that central area inside the coil. Then we're going to induce an EMF in the same coil because of that changing magnetic field. And of course, that induced EMF, according to Lenz's law, is going to oppose the change in that magnetic flux. So what that does is it slows the increase or works to maintain the original current to oppose a decrease. So what this is called is self-inductance. And what we are going to use for self-inductance is the letter L. So mutual inductance, letter M, self-inductance, letter L. And self-inductance, let's say we have n turns of wire. So maybe you only have one loop of wire, maybe you have 47 loops, is going to be related to that magnetic flux that it causes for itself and the current in the wire. So the EMF induced in the coil of self-inductance can be written, so this is just a rewriting of Faraday's law, right? As this change in flux over time, multiplied by how many loops we have, and then the negative sign lets us know that we are resisting that change. If I rearrange what we defined as our self-inductance, I can rearrange that to be self-inductance times the current in our loop divided by N. And so if I take a time derivative of that, which we should all be able to do with all our calculus classes, our self-inductance is not something that's changing. We're not changing the number of loops we have, and so all we're looking at is how current is changing with time, which is something we might know a little better. And so we put that into our EMF equation, and we get an equation that looks like NL divided by N di dt. Or, in other words, we get the relationship that our induced EMF as we change our current in a circuit looks like minus L times di dt. Our self-inductance is also in Henrys. And again, just like mutual inductance, L depends on geometry like size and shape and number of turns, and whether we've got an iron core. So ferromagnetic materials matter here. So whether it's an air core or an iron core or a steel core or something like that. So that leads us to another circuit element that we can talk about. So a coil that has significant self-inductance is called an inductor. So something we're not just going to ignore. The self-inductance of is an inductor. So this is designed. The symbol for an inductor looks, that's my drawing of it. There's a better picture in your book. Looks like a bunch of loops, right? So it looks kind of like a cartoon version of a solenoid. So that's our symbol for an inductor. Any resistance that an inductor has should be drawn in a circuit separately. So we'll get to that. So that we account for both of these things in separate places in our circuit. You can, if you want to avoid inductance, do something called a non-inductive winding. So you basically wind a coil back and forth on itself to cancel the magnetic field. You basically wind a coil this way and then turn it back the other way and wind back and forth like that in your column of stuff, right? So that would give you a way to cancel the magnetic field and cause little to no inductance. This is sometimes a good idea if you're trying to avoid heat caused by that inductance. All right, so for a given E, so for a given electromotive force, if you've got a large L inductance, what you're really doing, remember, you've got this relationship. If you've got a large inductance, you're going to create a small change in current. So if you've got a small L, you can have greater swings in current for that same given E. So a greater inductance is going to cause less AC. So it's going to cause a smoothing of any kind of fluctuations in your currents. Inductance is something like resistance to AC alternating current, right? And we're going to talk about reactance and impedance depending on inductance and frequency. So reactance and impedance are kind of like our resistance, but in an alternating current sense. So how about an example? Let's look at the inductance of a solenoid, because solenoids are pretty typical type inductors. So this is from your book. It's on page 972. It says, consider a uniformly wound solenoid having N turns and length L. Assume that length is much longer than the radius of the windings, and the core of the solenoid is air. So they want us to first find the inductance of the solenoid. So again, we're going to want to start by looking at flux. So we're going to look at the flux B through A, the cross-sectional area of the solenoid. Well, our solenoid is going to have a magnetic field that looks like mu 0 N times I, and then our area A. We could rewrite our lowercase n, again, remember that is turns per unit length. So we have however many capital N turns per the length of the solenoid. Right? And then we're going to use our equation for inductance. So our generic equation for inductance is N times flux over current. So if I do that, I end up with a mu 0 N squared divided by L times A. And that would be my answer for part A. Then it says, calculate the inductance of the solenoid if it contains 300 turns, its length is 25 centimeters, and its cross-sectional area, that should say area, is 4 centimeters squared. So what is this telling us? 300 turns, that's giving us N. Length is 25 centimeters. I'm going to switch that to SI units of meters. And we want to talk about its cross-sectional area, so they gave us an area. You might also be given something like its diameter instead. So I want to switch centimeters squared to meters squared. Remember, I have to cancel out centimeters twice. So remember, I've got in 1 meter 100 centimeters. I need to do that twice to get myself into meters squared. And so just to be sure, I've got 4 times 10 to the minus 4th instead of times 10 to the minus 2, because we are moving from units squared to units squared. Right? Okay, so silly little unit conversion stuff, but all of this information is going to go into the stuff I found in part A. The core of the solenoid is air, that's the mu 0. So our inductance for a solenoid that is this exact shape and size is going to look like 0.181 millihenries. Right, so putting all that in, I should have something that looks like, from all of this, Teslas times meters squared divided by amps, and those units convert to millihenries. The milli, of course, coming from my calculator spitting out a 10 to the minus 3. Okay, so that's one example of how to figure out inductance. It's not too hard. You just need to figure out flux for the specific thing you're talking about, and then use that to figure out your inductance, your self-inductance of this thing. So let's talk about the energy that gets stored in a magnetic field. So creating any kind of field is going to cause us to store energy, right? So if we just start out with an inductor that's got an inductance L carrying a current I, and that current is changing at a certain rate, we know that that inductor is using power. So P equals I times E. And we can talk about the self-inductance creating that EMF. So the self-inductance creating that EMF looks like this. So L times di dt. And here we're just doing the magnitude, so I've dropped that negative sign. So if we want to look at the work needed to increase the current from 0 to some non-zero value of I in the inductor, we do a little bit of work. That is how our power is changing through time, right? So that's why I use this power equation above. So if we're doing a little bit of work times power, or equaling power converting through time, then I've got something that looks like our inductance times our current times our rate of change of current. And of course, the dt has disappeared. So our work energy, or our total work that we need to do, we need to go from some zero current to some value of I. So we would do this integral. So the work that we do looks like 1/2 L I squared, right? L is just a constant in this integral up here. So I'm just doing this integral of I di from 0 to some value. All right, so our work energy theorem then would give us that this amount that we had to do to bring the current up to some value is the amount of energy that is now stored in the inductor. So the potential energy that is stored in the inductor looks like 1/2 L times I squared. So that's the energy stored in the inductor. If we take our potential energy to be 0, when our current is 0. So this is our potential energy stored in an inductor. You can go ahead and compare that to the potential energy stored in the electric field of a capacitor. That was 1/2 C times V squared, and you'll see that the form looks very similar.